Hello everyone, this video is going to walk you through basic stoichiometry calculations and follow that with percent yield calculations since they are closely related. Stoichiometry is a fun used word if you want to scare a grown-up. It is a long word, but it is a fancy name for a process that you use all the time. So let's look at an everyday example of stoichiometry. The day after big holiday dinners in my family, lots of folks would stay over at the house. And so the morning after, we always had blueberry muffins from a box. Not always Betty Crocker, but sometimes we sprung for the good stuff. And that was just what was for breakfast, as you wanted to get all of these relatives out of your house because you were tired of spending time with them. And my younger brother and I were always in charge of making the blueberry biscuits. And what that really meant was I was in charge of making blueberry biscuits for safety reasons. So let's say the box says that it makes enough for 12 people. This is a lie. It does not make enough for 12 people, but we'll take it at face value. But there are 18 people that you need to make muffins for. Excuse the random error message. There are 18 people that you need to make muffins for. So how many boxes of mix do you need, and how many cups of water do you need, since that's the first ingredient, right? If we have 18 people over, that's more than 12. So obviously we'll need to make some multiples of the box mix. And the recipe calls for 3/4 of a cup of water. Well, we're going to need more than that because we need more than one box. But how much do we need? So here's how a scientist would approach these calculations, figuring out how much materials they need. They would start with the fact that we know that there are 18 people that we need to prepare for. And they would then use dimensional analysis or railroad tracks and the ratios that are provided on the box in order to determine the correct amounts of each ingredient. So the box says it serves 12 people. So one box would be enough for 12 people, which is the first ratio that they used. 18 divided by 12 would give us 1.5 boxes. So we need the mix from 1.5 boxes in order to make muffins to feed everyone. Another ratio is that in order to make one box of mix, you need 3/4 of a cup of water. Well, first of all, we don't muck around with fractions in science. That would be 0.75 cups of water. And so when we add that ratio on to our railroad tracks, 18 times 0.75 divided by 12 is 1.125 cups of water. So that would tell us exactly how many cups of water we need in order to create the correct amount of muffins. In scientific equations, we do not have recipe boxes with mix amounts on the outside of the box. Instead, what we have are balanced chemical reaction equations. And in the first half of this unit, we learned to create these by using the coefficients to describe individual molecules. However, they can also be used to describe moles of molecules. Remember that a mole is a word for a large number of molecules, Avogadro's number of molecules. And so just like on the box, there are multiple substances involved in the reaction equation. Here we have the reaction equation for aluminum and copper 1 chloride reacting to produce copper metal and aluminum chloride. And just like I made a ratio from the recipe box saying that one box calls for 3/4 of a cup of water, I can make a ratio saying that for every 1 mole of aluminum that is put into this reaction, you get out 3 moles of copper metal. And those numbers came from the coefficients in the balanced chemical reaction equation. We always write these ratios using 2 materials at a time, in this case the aluminum and the copper. But because there are more than two materials in our reaction equation, we can write different ratios using the same equation. So for example, if I wanted to know the ratio between copper 1 chloride and aluminum chloride, I would say that there are 3 moles of copper 1 chloride for every 1 mole of aluminum chloride. Again, these numbers come from the balanced chemical reaction equation. These ratios are not the only ratios that we use in stoichiometry. So let's look at the generic form of the most common. The most common stoichiometry that you'll be asked to do is mass to mass. This is where we start with the mass of, for example, aluminum, and we end with the mass of a different material. We could end with the mass of copper. So this type of problem in its dimensional analysis will start with the mass given in the problem and end with the mass of the new material that is being asked about. There are 3 ratios: the molar mass of the first substance, the mole ratio, which we just talked about how to create using the balanced chemical reaction equation, and then the molar mass of the new substance. The only thing that is new in these railroad tracks would be the mole ratio. We have learned previously in several units about using the periodic table to look up the molar mass of various substances. So let's look at a more specific example of this type of problem. Back to our reaction between aluminum and copper 1 chloride, we are asked 2.15 grams of copper 1 chloride are reacted to produce how much copper? So like I said, we're given a number in the problem, 2.15 grams of copper 1 chloride, and so that is where I start my railroad tracks. The first ratio is the molar mass of that copper chloride that we are asked about in the problem. And we determine this by looking at the periodic table and adding up the mass of copper and chlorine. There's only one of each in the formula, so we only need 1 copper and 1 chlorine, and that adds up to 99 grams of copper chloride in 1 mole. So that's where our first ratio comes from, off the periodic table. Our second ratio comes from the balanced chemical reaction equation, right? And so there's a 3 in front of copper chloride and a 3 in front of copper. So we're going to place the 3 moles of copper chloride and the 3 moles of copper into our dimensional analysis. Some people would try and simplify this ratio to 1-to-1. I do not recommend doing that. Just to avoid any possible silly mistakes, I would copy the ratio exactly as it appears in the balanced chemical reaction equation, just to make sure we don't make any simplifying errors there. Our final ratio again comes from the periodic table. It is the molar mass, this time of the new material, of the copper. Because copper is an element and there's only 1 atom in the formula, we can pull 63.55 grams directly off of the periodic table and plop it into our dimensional analysis. Now that we have determined the mass of copper, grams of copper is the only unit that doesn't cancel in this dimensional analysis, we are ready to go into our calculator. So we'll type in 2.15 times 3 times 63.55. We'll divide by 99 and divide by 3, and we should get 1.38 grams of copper. This is good because it has the same number of significant figures as 2.15 grams that we started with, 3 sig figs each. And so that means we are all done with our problem. So this is how you do basic stoichiometry. And so we talked about a real-life example of stoichiometry. We looked at how do you create mole-mole ratios using balanced chemical reaction equations, and we looked at the generic and a specific example of the basic stoichiometry problem. Once you have finished your stoichiometry problem, a question that often accompanies them is called a percent yield. And so what the percent yield is, now that you know you were supposed to collect 1.38 grams of copper, how much do you actually collect? Okay, so just like on an exam, when you should earn 100% of you should earn 100 points, but how many points did you actually earn? This is what we're getting at with our percentage calculation here. I had a lab chemistry course in college where that was your grade percentage, right? Whatever your percent yield was your score for that lab. So in our example that we just looked at, you should have collected 1.38 grams of copper, but you went to the lab, you put in the experiment, and you only measured out 1.26 grams of copper when you were all done. And so the question now is, what percentage of the expected result did you actually collect? So just like in our previous percentage calculations, we take part over whole times 100 to calculate our percent. 1.26 was the part that you actually collected. 1.38 was the total of what should have been there. We're going to multiply that by 100 and we get 91.3%. So if this had been my grade in my college lab class, I would have been pretty happy with that. Pretty much in the real world, pretty much anything over 80% yield is considered good. If you start dipping below 75%, people start asking questions because chemicals are expensive and the companies that chemists work for don't want to waste a bunch of expensive chemical with low percent yields. So this is kind of an add-on to a basic stoichiometry question. They'll ask, how much are you supposed to collect at the end of the problem? And then if you actually get this, what is your percentage? And so you would do the basic stoichiometry problem first, and then you would kind of add on this percent yield problem. Okay, so that tells you about how to do basic stoichiometry problems as well as percent yield add-ons. Thanks very much and have a nice day.